All right, so picking up where we left off on the chapter review, we want to graph each polynomial function and then fill in the missing information. So starting with end behavior, informally, the end behavior is based off of x to the third. Because this is a positive x to the third, the right side goes up, and the left side does the opposite because of the odd exponent. So this is informally the end behavior. Using that visual, I want to use limit notation. So to describe the left, you need to say the limit as x approaches negative infinity of, I'm just going to say y, because that's what it's called, is equal to negative infinity. So this means the left side of y goes down. And then the limit as x approaches infinity of y is equal to, this goes up, so positive infinity. So this means the right side of y goes up. You have to use the correct limit notation. You can't put your own spin on it. Exactly how I've written it with the, you don't have to have the cursive L, but everything else should be the same. That's how you have to write it. It's not just a different version of what you wrote in Algebra 2. You have to write it this way for the AP test. Okay, complex zeros. Remember, that just means all zeros. So if I want to find the zeros, I should set the equation equal to 0, and I should begin factoring. So I can factor by grouping here. Take out an x squared, and you have x plus 2. Factor out a minus 1 from the last two terms, and you also have x plus 2. There's now a GCF of x plus 2, and that leaves you with x squared minus 1. And then that can factor further. So x plus 2, x plus 1, x minus 1. So the zeros are negative 2 and plus or minus 1. Okay. Sorry, I want to box in my other answers here. So the first thing you should do is plot those zeros. The y-intercept for any function, the y-intercept is what you get when you plug 0 in. So I was going to write f of 0, but this is y. So y of 0 is equal to 0 plus 0 plus 0 minus 2. So y equals negative 2. You should plot that as well. And the nice thing about that is that we don't have any points, any integer points between our values. So we're not going to have to plug in any extra points here. And then for what intervals is y greater than or equal to 0? So let's graph this first, and then we'll consult our graph. All right, so sketching the end behavior, I usually start with that, something small. And then the graph is changing signs at every x coordinate because the multiplicity is 1. So the graph is crossing through at all of these. So something like this. And again, I'm not sure exactly how far this dips up or down, or if the graph really comes down a bit more to here. I'm just not having you be that accurate. And then for what intervals is y greater than or equal to 0? So remember, this just means positive or above the x-axis. So that would be this little section here. So from negative 2 to negative 1, the graph is greater than or equal to 0. And then from 1 to infinity. And I'm including those endpoints because it says greater than or equal to. The second equation is already in factored form, so that makes finding the zeros really easy, but we do have to think a little bit about end behavior. So think about what you would have if you FOILed this together, but you don't actually have to FOIL it together. So I would have negative x squared times x times x. So what does that come out to? Negative x to the fourth. And there would be some other terms, but we only care about the leading coefficient, the leading term there. So the end behavior, because this is negative x to the fourth, is down on the right. And because it's an even exponent, the left side has the same behavior as the right. So both sides go down. And then to say that, we could say the limit as x approaches negative infinity of y is equal to negative infinity. So the left side of y goes down. And the limit as x approaches infinity of y is equal to infinity. The right side of y, is equal to negative infinity, goes down as well. So both of those are negative. Make that a little more clear. There we go. For the zeros, again, you're just setting this expression equal to 0. It's already factored for you. So the zeros are x equals 0 from the negative x squared and plus or minus 2. So we can plot those. Negative 2, 0, positive 2. The y-intercept we already have. It's 0, 0. But it is what you would get if you plugged 0 in. That'd be 0 times 2 times negative 2. Still 0. And we need to graph to be able to answer this question. For what intervals is y less than or equal to 0, which will mean under the x-axis or negative. All right, so the end behavior is down. The graph should be bouncing at 0 and then crossing through at 2 and negative 2. And I do have some extra points to put in here. I want to know how high up the graph needs to go. So I'm going to plug in negative 1 into the function and see what I get. So into negative x squared. So I plugged in negative 1. Now, negative 1 squared is 1, but then you multiply it by this negative. So that leading term is still negative 1 times 1 times negative 3. That's positive 3. So plot up here. And this is an even function, so I do know that at 1 I'm going to get the same thing, but I can show that. Plug in 1, and you get negative 1 squared times 1 plus 2 times 1 minus 2. So that's going to be the same thing. Negative 1 times 3 times negative 1 is still positive 3. And then I can connect these. And I meant for that to be a smooth curve, sorry. Get a little more precise here. There we go. You want your graphs to be, rounded and smooth. I'm not going to be too picky about this, but I just didn't want mine to look kind of linear like it was. Okay, so let's answer this question. For what intervals is y less than or equal to 0? So it's below the x-axis on the ends, and then don't forget equal to 0 also at 0. So I'm going to say negative infinity up to negative 2, also at 0. You could also use square braces here. And then also at 2 to infinity. Okay. Use the remainder theorem to evaluate each function. What is the traditional way to evaluate a function? So traditional way is plug in the number for x. But the remainder theorem, remember it says you're putting in the, I'm going to call it the c value. You're putting in whatever the value you're trying to evaluate, and whatever you get right here is the answer. Okay, so I'm going to put negative 2 outside of synthetic division. I'm going to set up synthetic division and pay attention to if you're missing any terms. We're missing a 0x squared, so we need a placeholder there. If we don't do that, then we'll get the wrong answer. So we drop down the 5, multiply negative 2 times 5, add 0 plus negative 10, multiply negative 2 times negative 10, add 6 plus 20, multiply negative 2 times 26, add 8 plus negative 52. What is that? Negative 44. Yeah. And again, this is the answer. So f of negative 2 is equal to negative 44. If you had extra time left over, you could go back and check. It should be that 5 times negative 8 plus 6 times negative 2 plus 8, that should also equal negative 44. So it's not that one is always easier than the other, but this is just kind of a nice way to evaluate a function as well. Okay, for this one, we have negative 2/3 outside our fraction. Not missing any terms here. 6, 10, 5, 1, and 1. Drop down the 6. Now remember, when you multiply negative 2/3 times 6, you should be doing the division first. 6 divided by 3 is 2. Negative 2 times 2 is negative 4. Add that to get 6. Okay, we just did this, so that's negative 4 again. 5 plus negative 4 is 1. Add that to get negative 2/3. 1 plus negative 2/3 is 1/3. Negative 2/3 times positive 1/3 is negative 2/9. And 1 minus 2/9 is 7/9. Okay, so f of negative 2/3 is equal to 7/9. Now that, I will say, was definitely easier than what I would have to do if I plugged negative 2/3 in traditionally. Having to raise that fraction to an exponent and deal with that for all the terms would have probably been more time consuming. Write an equation of a polynomial function with the given zeros in both factored form, which is parentheses, and polynomial or general form, which is, multiplying out all the terms. Okay, so we need to have a degree of 3, zeros of 3 and 2i, which really we know means plus or minus 2i. So always begin with factored form. I'm going to write f of x equals, for a 0 of 3, that's x minus 3. Zeros of plus or minus 2i, x plus 2i, x minus 2i. Multiply the conjugates together first. Now, you might know, because we've been doing this for a while, that x plus or minus 2i is how you would factor x squared plus 4. But if you don't know, remember, you can always do this. X equals plus or minus 2i. Square both sides. X squared equals 4i squared, which is negative 4. Add that to get 0. So that's how you get that factor. And then we need to multiply this through, so I'm going to distribute the x through. I'm going to distribute the negative 3 through. And then I'll just write my final answer in standard form, just so everything's in order. So this is the general form, or the polynomial form of that equation, and this was the factored form. Okay, the second one is harder because we're given a point that we have to satisfy, so degree 3. Zeros are 2 and negative 1, where 2 has a multiplicity of 2, so that's kind of nice that we don't have any imaginaries. And then f of 1 equals 18. Remember, this is something that means you have to figure out an a value that's out in front of your factored form. Okay, so let's begin with the zeros that we're given. So we don't know this a value. Zeros are 2 and negative 1, where 2 has a multiplicity of 2. So that means x minus 2, that's the factor that x equals 2 came from, has to be squared. And then a 0 of negative 1 means x plus 1 was the factor. So that's not too bad. And we can start foiling that out, right? So we could say, let's see, this is x squared minus 4x plus 4 times x plus 1. That's x cubed minus 4x squared plus 4x. Multiply the 1 through. Plus x squared minus 4x plus 4. Clean it up. X cubed, let's see, negative 4 plus 1 is minus 3x squared. Plus 4x minus 4x cancels. Plus 4. Okay, and to find a, we're going to say when you plug in 1 for x, you get 18 for y. So set the equation equal to 18 and plug in 1 for x. So this becomes negative 2 plus 4 is 2. A times 2 equals 18. So a equals 9. All right, so factored form, I now know that that's f of x equals 9 times x minus 2 squared times x plus 1. There's factored form. General form, just to go back here and say f of x is equal to, what do I get if I distribute a 9 through? 9x cubed minus 27x squared. 9 times 4 is plus 36. Okay, we've got time for just a couple more then before office hours start here, and then we'll finish this in a third video here. Remember, we're spending 2 days in class working on all of this. Find all complex zeros. Write the linear factorization for each function. So that means that you might have factors that have i's in them or radicals. So starting with x squared plus 36, If you're having trouble with this, find the zeros first. You don't have to factor first. So you can say 0 equals x squared plus 36. Negative 36 equals x squared. Square root both sides. You get plus or minus 6i equals x. So the zeros are plus or minus 6i. And then the factored form is f of x equals x plus 6i, x minus 6i. For this one, let's see, are we going to get any factors where we put in 2x and x and 5 and 1 or 5 and 1? I don't think there's any way to get 1 in the middle, right? Because you get 10 and 1 or 5 and 2. Nope. So this does not factor, which means to find the zeros, we need to use the quadratic formula. So x equals negative 1 plus or minus square root of 1 squared minus 4 times 2 times 5 all over 2 times 2. And then we need to do the math underneath the radical. So negative 1 plus or minus. This is 1 minus 40, so the square root of negative 39. And 39 is 3 times 13. Neither of those numbers are perfect squares, so we just need to take the negative out. So negative 1 plus or minus I radical 39 all over 4. All right, so those are the zeros. Oh, actually, sorry. So I have room to put my work here. So negative 1 plus or minus I radical 39 all over 4. So that's a pretty ugly set of zeros to write in factored form, but we can still do it. Factored form is just x minus the 0. So you can say f of x, linear factorization would just be x minus, and then I'm just going to write this expression, negative 1 plus I radical 39 over 4, and x minus negative 1 minus radical 39. Oh, I. Minus I radical 39 over 4. The minus, I'm leaving it out here. You don't want to make it plus positive 1 without distributing the negative through. So just leave it like that. I mean, I guess if you did that, it would still technically be right, but you just have to be careful because technically you should be distributing the negative through. Okay, and then what about this one? So this does factor to begin with. We've had this in a speed quiz before. Numbers, break up x to the fourth by making it x squared and x squared. Break up 16 with 4 and 4. And you need to add to negative 8, so minus and minus. So this would be x plus 2, x minus 2, x plus 2, x minus 2. So I'm just going to write x plus 2 squared, x minus 2 squared. So that's actually the linear factorization. And then the zeros are x equals plus or minus 2. All right, I'm going to finish out. Well, no, I'm going to stop the video here. And then the next video, we'll pick up with the rest of the review.